-4 using polynomial roots. So our goals today are that we can graph a polynomial function using our graphing calculator. We can write a polynomial function in factored form given a graph or its solutions. And we will be able to determine how many real and imaginary roots a function has. Okay, so first thing we're going to do is graph the function in our graphing calculator. And it says to identify the roots, the relative minimums, and maximums. So we're going to go ahead and pull up our calculators. And then I typed this function into my calculator already in the y equals screen. And then we're going to hit graph. Okay, so we get the picture of our graph. And previously we just kind of did a rough sketch of this. Today we're going to actually write down what the roots are and the relative minimums and maximums. So there's a couple ways to do this in the calculator. The easiest way is just clicking trace right here. And then that gives you this little cursor that pops up. And then you can move that cursor along your function. And it's not going to be 100% perfect, but we can get pretty close. So remember, roots are the solution, so where it crosses the x-axis. And it looks to me like this approximately crosses the x-axis at about a -1.2. So I would say our first root is at -1.2, 0. And that's not perfect, but it's a pretty good estimate. Okay, then if I move my cursor to the next place it crosses the x-axis, that's at approximately 1.8. So our next root is at approximately 1.8, 0. And then we have a third root, a third place it crosses the x-axis. So if I move my cursor, looks like that's at approximately 3.3. Okay, so those are all of our roots. A relative minimum is like a low point on the graph, and the reason it's called a relative minimum is because it's not truly the minimum. So this point right here, this low bump on the graph, is a relative minimum, and it's not really a minimum because this graph keeps going down and down forever. So we have only one relative minimum, and sometimes you might have multiple if there's like multiple bumps in the graph. We have one relative minimum at 0, -7. And then if we go back to our graph, we have one relative maximum up here. So I'm going to move my cursor to that. And it looks like that's about our relative maximum. And so that's at about 2.7, 2.5. Okay, so now I'm going to use these points to try to make a pretty accurate graph. So -1.2 would be about here, 1.8, and then 3.3. Those are the roots. And then here's my relative minimum, and then my relative maximum. Okay, and then we're gonna draw in our function, which let's see how I can do on this. Okay, we get the idea. Hopefully you can do a little bit better on your paper than I can do on this tablet. So then we can get a sketch of our graph, and then solutions. Remember, the solutions are like the roots, it's where it crosses the x-axis, except solutions we usually write as x equals. Okay, so x equals -1.2. So same values we found up here already. X is equal to 1.8. and x is equal to 3.3 would be our three solutions of this graph. Okay, for sake of time in this video, I'm going to skip this problem if you're looking at the note sheet, and we're going to go on to this problem. So I'm going to relate this back to quadratic functions, to parabolas, because that's what we're most familiar with. So it says, what are the solutions to this quadratic equation in factored form? So I took this original quadratic equation and I factored it. So this right here is factored form. So we should be really familiar with factoring and solving. So remember, to solve this, we would set each of these equal to 0. And we would get a solution of x is equal to 2 and x is equal to -1. Okay, so something that is important here, that I know a lot of us have already started to see this pattern, is that the sign of the solution is always switched from the factor. So for example, this solution's a positive 2, but the factor was an x minus 2. This solution is a negative 1, but the factor was an x plus 1. Okay, so that'll be important whenever we're writing in factored form. Now, last thing I want to connect this to is these solutions on a graph. So, we got our solutions from factored form, and then remember those solutions on the graph is just where it crosses the x-axis. So we got a solution of x equals 2, which we also found from factored form, and x equals negative 1, which we also found from factored form. Okay, so we're going to take this same factored form, x minus 2, x plus 1, but what if we have a different a value? So it says if the function has a different a value, does that affect the solutions? So if we look at our graph, because of this a value, our graph is now upside down, but our solutions still cross at x equals positive 2 and x equals negative 1, which is the same thing here. If I set these equal to 0, I get x is equal to 2 and x is equal to negative 1. So my a value is not going to affect those solutions. Sure, it makes the parabola look different, it's upside down, but that a value doesn't change what the solutions would be. The factored form still gives us the solutions. Okay, so we're going to look at some different polynomials now because we're super familiar with quadratics, so we're going to look at some different polynomials. It says to give the equation for the graphs in factored form. And then just a reminder, if it wants an equation, remember that has to have an equal sign. So a y equals. Okay? So first thing you want to do is figure out what are the solutions to the function. And then once you have the solutions, you can write it in factored form. So our solutions to this is x equals negative 4. Remember, that's just where it crosses the x-axis. X equals negative 3, x equals 0, and x equals 1. So then, if we take those solutions now and write in factored form, so I need to have y equals, and if my solution is x equals negative 4, then remember my factor would be x plus 4. Because if I were to set this equal to 0, and then subtract 4, that's why that sign is different, okay? So the factor is x plus 4. My solution is negative 3, so my factor would be x plus 3. 0, you can write x plus 0 or x minus 0, or you could technically just write x, but you do need to have an x. And then x equals 1, we would have a solution of x minus 1. Whoops, that doesn't look very clear. X minus 1. Okay, so then last thing you need to ask yourself, because we know that the a value doesn't really affect the solution, but one thing we do want to think about is if our leading coefficient, so if our leading coefficient is negative or positive. And so since both ends of this graph are going down, our leading coefficient is going to be negative. That's something we talked about in our 3-3 notes. Okay, so why don't you guys try this equation here, look at this equation, find its solution, write it in factored form like we did with this graph. All right, moving on to something called the fundamental theorem of algebra. So this is really important. This is actually what told us mathematicians a long time ago that there were even imaginary solutions. So this is from the textbook, and we'll summarize this in a second. But it says a polynomial equation of degree n has exactly n roots, which remember the name roots is the same thing as solutions. And the set of complex numbers, which complex numbers are real and imaginary, including repeated roots. And we'll talk about next slide what a repeated root is. So if we look here, this is a degree of 3, x cubed, and we have 3 roots. This is a degree of 4, and we have 4 roots. This is a degree of 5, and we have 5 roots. Okay? So essentially what this theorem tells us is that the degree tells you how many solutions, which solutions, roots, zeros all mean the same thing. So it tells you how many solutions, roots, zeros a function has. And remember, those can be real and imaginary solutions. Okay? So make sure we have this written down. This is the official words from the textbook, but then this is kind of summarizing what the fundamental theorem of algebra tells us. Okay, so let's talk about this idea of what is a repeated root. What is it talking about there? So I have a couple of examples of what repeated roots look like. So if we look at this first example here, we have an equation and we have a repeated root right here because we have 2 factors of x plus 2. So if I have a factor of x plus 2, that's going to be x equals -2, solution of x equals -2. So I have right here x equals -2 twice. It repeats. Okay? But then x equals 1 is only one solution because there's only one parentheses. So this is one example of what a repeated root looks like. So I like to say that this like bounces off the x-axis. Okay, so this is one example of what a repeated root looks like, where it like comes up, it hits the x-axis, and then comes back down. Okay. If we look at this example, so I have x equals 8 just a single time right here. But then we have x equals 5, x equals 5, x equals 5. So this solution at x equals 5 repeats. And in this example, this is repeating 3 times, okay? So this is what this is going to look like when it repeats. So this was what it looks like if it repeats twice. This is what it's going to repeat when it repeats 3 times. So if you guys notice, and let me kind of erase this point, the function comes down, it hits the x-axis, and then it like flattens out on the x-axis, but then it does go through it, okay? Whereas when just one solution, it just goes straight through the x-axis. So I like to say that this like flattens out on the x-axis. Okay, so that's another example of what a repeated root would look like. Okay, so let's look at some examples of putting these ideas together. Because knowing this information, we can tell how many solutions a function should have, and then know how many real and how many are imaginary. So it tells us to use the graph and the equation to answer the following question. So we have an equation up here, and we have its graph down here. So A says how many solutions should there be? So we want to look at the degree for that. So there should be 4 solutions because it's a degree of 4. Okay? Then B says how many solutions are real? So remember, the real solutions are going to be where the function crosses the x-axis. Only 2 of those are real, and that's where it crosses the x-axis. Okay, so now it says do any repeat. Remember, repeated solutions are these 2 scenarios. So where it bounces off the x-axis or it flattens on the x-axis. So that's not happening here. It's not bouncing off the x-axis. It's not flattening on the x-axis. So none of these repeat. So therefore, if 4 solutions must exist and only 2 of those are real, then how many are imaginary? 2 of those must be imaginary. Okay. Let's go ahead and look at this next one. So same directions, we're going to use this equation and this graph to answer our questions. So how many solutions should there be? Again, I have a degree of 3, so I should have 3 solutions. How many solutions are real? Well, I see where it hits the x-axis 2 times here. We have x equals 2 and we have x equals 5. So I'm going to say 2 of them are real. Do any solutions repeat? So right here, this right here repeats. Okay? Because it bounces off the x-axis. So really, I have 2 solutions of x equals 5 right here. Okay? So I have x equals 5 twice, and I have x equals 2. So then it says how many solutions are imaginary? Well, none of those are imaginary because really I have all 3 solutions. 2 of them are just x equals 5 because that's repeating, and then 1 of them is x equals 2. All 3 of my solutions exist right here, so none of them are imaginary. Okay, and then last thing I want to do with this one, and this I don't think part E is on your note sheet, so just add this in. It says write the equation in factored form. So remember our solutions, and I'll come back to the leading coefficient. So if my solution is x equals 2, then my factor is x minus 2. And then the reason I wanted to add this in is because if the solution is x equals 5 twice, I really have to have x minus 5 twice, okay? We can't just write it once because really that solution does exist twice. This is a degree of 3, so you must have 3 parentheses for this to be a degree of 3 because x times x times x is x cubed. Okay, and then my leading coefficient, since the function is ending going down, that would be a negative. Okay, last piece we need to do is talk about when we're given our solutions in words rather than from a graph. So it says give the equation for a polynomial in standard form with the following solutions. Okay, so it tells me that we have solutions of x equals 5, x equals negative 2, but a multiplicity of 2. So multiplicity of 2 means this solution repeats twice. Okay, that's what multiplicity of 2 means. So when I write this equation, I would have x minus 5 as one of my factors, and then I would have x plus 2 twice. Okay? And it just says give it for a polynomial in standard form, so we can just assume our leading coefficient would be a 1. Now, we want this in standard form, so we're going to have to multiply this out. And I'm going to skip a little bit of steps to just, for simplicity, to shorten this video a little bit. But I went ahead and double distributed this first, and you would get x squared plus 4x plus 4. And I just did these two first because multiplying x plus 2 times x plus 2 is pretty easy. But you could have multiplied these first two. Then I'm going to go ahead and distribute this out and combine like terms. And after I did that, I got x to the third minus 1x squared minus 16x minus 20. Okay, and then this is my polynomial in standard form. Make sure you do have y equals because it wants an equation. All right, last important piece of today's notes is another theorem, and it's called the complex conjugates theorem. So what this says is let a and b be real numbers, and b cannot be 0. If a plus bi, so a plus bi, remember, is real plus imaginary, is a 0, so a solution of a polynomial function with real coefficients, then a minus bi is also a solution. So what this is saying in this example is if you know that 3 plus 4i is a solution of some function, then 3 minus 4i must also be a solution. Okay? So it tells us to write an equation of the polynomial function in standard form with zeros of 1 and 2i. So what this is saying is we have solutions at x equals 1. We have solutions at x equals 2i. But then we also have solutions at x equals negative 2i, okay, because of this theorem. If a plus bi, so in this case my a is 0, so if 0 plus 2i is a solution, then 0 minus 2i must also be a solution because of this theorem. Okay, so I'm going to write this in factored form. So I'd have x minus 1, and then I'd have x minus 2i and x plus 2i. All right, so what I would do first is multiply these out that have these two. Oops, I'm going to bring down the x minus 1. And I'm going to multiply these out that have both imaginaries. Okay, so x times x is x squared. X times 2i would be 2ix. This would be minus 2ix, and then this would be minus 4i squared. And then in here, 2ix minus 2ix would cancel. And then remember, I squared is equal to negative 1. So this is really negative 4 times negative 1. So this is really positive 4. So let's clean this up. I'd have x minus 1 and then times x squared plus 4. Okay, but that is still not in standard form. And so again, I'm going to skip a step just because this video is getting a little long. And we would just now distribute this out again. And when we do that, we would get y is equal to x cubed minus x squared plus 4x minus 4, okay? And you know, if we were to look at this function, like if you were to graph this function in Desmos or your graphing calculator, this function is going to have imaginary solutions because it only really crossed the x-axis at one real value. So you'd have one real solution on your function, and then you would have two places that does not actually cross the x-axis.